Hello, so my name's Anna Slater. I'm a postdoctoral researcher in chemistry. It's my job to make new molecules. That's what I do for a living. And I'm going to talk to you today about how we can build structures with those molecules, how we might be able to go from this situation on the left, we've got a jumble of building blocks, to this situation on the right, where we've made something complex and perhaps useful, but on a very, very small scale, and why we might want to do that. So this concept was really first popularized, the concept of nanotechnology and nanochemistry, by this guy, Richard Feynman, in his Christmas lecture. I'm going to say Christmas lecture, it's around about December 1959, entitled There's Plenty of Room at the Bottom. And if you had a little giggle about that, you're not alone. I still find this funny after giving this lecture many times. He talked about the challenges and the opportunities that exist when you try to build structures out of extremely small things. And he used the example of DNA, saying that in the tiniest cell, all of the information for the organization of a complex creature such as ourselves is stored. So there's an estimate that says that for every bit of information about a person, you need about 50 atoms of DNA. He also said that if you could maybe do this artificially and store a bit of information on a piece of material, say 10 atoms by 10 atoms, you could fit the entirety of human knowledge and everything that has ever been published on a piece of material that's a millimeter by a millimeter. So the miniaturization of information and storage of information is one of the main motivators for working in this area. But you can also think about, if you make an extremely small structure, maybe you can start to interact with the molecules that make up nature and biology and DNA. So there's a lot of motivation for doing this. And the first time I really got involved in this area was when I applied for my university place. So I sent out my UCAS application, and it went to this guy in Nottingham. This is Neil Champness. He's a professor of chemical nanoscience. And he showed me this image at my interview and said, this is a scanning tunneling microscope image of molecules. Every white blob on this structure, which I hope you can see, is a molecule. And I thought, that's really cool. You think of chemicals as coming in bottles or bubbling away in beakers, but every one of those is a molecule. And they've arranged themselves through self-assembly into a honeycomb network. So I thought this was so cool that 4 years later I accepted a PhD position in Neil's group working on building with molecules at the nanoscale. So how small are we talking? I keep saying nano. I'm guessing a lot of you will know that a nanometer is 1 × 10⁻⁹ meters. Just going to put that in context for you. A human hair, something we think of as being extremely small, is 80,000 nanometers. Okay? A red blood cell, 7,000 nanometers. So we're talking about molecules that are about a nanometer across. So this is C60 on that end there. It's about a nanometer. It's a circular molecule shaped like a, not spherical I should say, shaped like a football. And that's the kind of length scale that we're working on. So can you really build things out of things that are this small? Well, you can. Here's an example of some work that was done in IBM in 1993 of iron atoms on a surface. And they individually moved these iron atoms into this little quantum corral, that's what they call it. It's a little circle. It's about 48 iron atoms in there. There are issues with working on this sort of scale, though. First of all, it's incredibly time-consuming to move individual atoms, right? You can't sit there and do this for hundreds or thousands, or if you wanted to store a gigabyte of information, you're going to need to be sat there for quite a long time with your STM chip. And secondly, when you're working at these very small scales, forces like surface tension and the electrostatic interactions that are present between every molecule are big problems, so you feel these forces very strongly. It's kind of like trying to build something out of Lego that somebody has covered in honey. It all sticks together and not necessarily in the way that you want. Thankfully, we can take some inspiration from nature for some solutions to these problems as well. So if you don't want to sit there and individually move every atom and molecule you're working with, you can use self-assembly. You can design a system where when you move the components close enough together, they stick, they arrange into the way that you want them to. And this is exactly what DNA does, which uses self-assembly. And if all your Legos stuck together, well, you can design molecules that can recognize each other. So even if somebody had covered your entire Lego set in honey, you'd still be able to make a tower because I found out today that they're called studs on the top of Lego blocks. I didn't know that, but they are. Studs on the top of Lego blocks that fit in the holes underneath. So even if you end up with a honey-covered tower, you can still build with them because you have that strong directional interaction. So how might you make a honeycomb network out of molecules? Going back to the image that Neil showed me. Well, if you take a molecule that's shaped like a rod and has 2 connecting ends, and a molecule that's shaped a bit like a triangle and has 3 connecting ends, and you move them close together, these particular molecules can form hydrogen bonds between them. So this is the same force that the DNA uses, hydrogen bonding. So it's this directional interaction that I'm talking about. It means that they're essentially puzzle pieces. So this one fits into this one. So if you plonk them down on a surface and you give them a little bit of energy to move around, you might find that 3 of them stick together like that. Maybe move them around a little bit more, you might have made a hexagon. Put a few more molecules down, and you can start to see how you might be able to build this honeycomb network like that. What can you then do with this honeycomb structure now that you've got it? Well, now you have a surface where some of it is covered with molecules and some of it isn't. So if you put down another molecule, like C60, which I was talking about earlier, that spherical shaped molecule, it will selectively go in the pores and sit where you want them to, like so. So now you have control over where you're putting these molecules down, which is a really nice step towards making complex structures. And here is another STM image. Again, I hope you can see it, where you can just about see this honeycomb network in the background. That's the light grey stuff. And here you've got little pockets of 7 C60s arranged into these pockets like that. So we've built a structure out of molecules. For me, this raises a couple of questions. One, is it always that simple? I've made it sound very easy. No, it's not. My entire PhD could be summed up by this sentence. So, if you make even a slight change to the molecules that you put in to build your structure, you can get a very different self-assembly pattern. Here's some examples. You can get ones that behave quite well. You can get ones that look a bit different. So this is using the same molecules. And you can get ones that just don't go well at all. The really nice thing about this area is every time you make a new pattern, you learn something about how to build with molecules. You iterate the process, try again. You've got more information this time. You can start to design the molecules that you think will make the pattern that you want. The next question that came to mind for me is, are we limited to 2 dimensions? Do we have to stay on the surface? Well, no, you don't. And in 3 dimensions, things get really interesting. And this is where I moved to Liverpool University to take up a position in the Cooper group. So this is my boss here, Andy Cooper. And this is a group of people who I work with over in chemistry. That's me before I got enormous. So, anyway. So within the Cooper group, we work with these molecules. These are porous organic cages. And this is just a 3-dimensional puzzle piece, like the 2-dimensional puzzle pieces I was talking about earlier. But they have a hole in the middle. There's sort of like a molecular sponge. You can fit gases in here. You can fit small molecules in here. It's just about a nanometer in diameter again. And if I freeze it, I've gone with a little Christmas colour scheme here. This is my nod to Christmas. You take one of these, put another one next to it, you can see how they fit together. You've got this recognition again, so they just clip together like puzzle pieces. You put a few more in, and actually, I mean, if you end up with millions more, you end up with this structure where you've got holes going all the way through it. So you've made yourself a molecular sponge simply by building with molecules. So these things are porous. They take up gases. So hydrogen, CO2, methane, nitrogen. They take up gases. They're also selective. So because the pores are a very certain size, and we can understand what that size is by using X-ray crystallography and characterization techniques, you can start thinking about how if you've got something that's too big for those pores, it won't fit into your structure, whereas something that is small enough will go through. So you can start separating things based only on their size. And they're customizable. They don't have to be that shape. You can spend do a lot of the same tricks we did in 2 dimensions in 3. So here's an example of some cages that have been synthesized by the Cooper group over the last few years. And there are also other research groups out there who are also working on these things. You can get a real nice diversity and variety of structures. So again, the really nice thing about this is every time you build a material out of these porous organic cages, you learn more about how to build with molecules. But now you're also getting materials that you can do something with a real-world application because they're porous and because they're selective. And this is one example. I haven't got time to tell you about all of the things you could do with them, but this is one example of something you can do. You can use these cages to separate krypton from xenon. So these are noble gases. They're basically spherical. They're very hard to discriminate against by normal methods. They have similar boiling points. The nuclear industry normally uses cryogenic distillation, which is very expensive to separate them. But it turns out that the cage I just showed you is almost a perfect fit for xenon. So you can separate the two just because they're a slightly different size really efficiently just by passing them through. It's a nice application. You can also separate out radon, which is another noble gas of interest, radioactive gas. So are we there yet? I mean, are we really making DNA? Well, I have to say, we're a long way from artificial DNA. That's not quite where we are, unfortunately. But we are at a situation where we can take a couple of these porous organic cages and make some really quite intricate structures that have some targeted properties that we're really looking for. And that's, again, what I love. I mean, I love all the variety that involves in working in this project. I do organic chemistry, I do physical characterization, I do a number of different things. And the best bit about it is I work with a really talented team of people. So massive acknowledgements to everybody on this slide and a lot more besides. Neil Champness and all the group at Nottingham that I used to work with. I'll say thanks to LiveWise and thank you for all listening.